All right, guys, welcome to another episode of Cuda Education. Today, I wanted to clean up some of our discussions and also talk about fences. Okay, so um, let's just get into it. This is Cuda Education. If you want to be able to run these examples, get tutorial number 1 and tutorial number 13. They are in the description below. Tutorial number 1 is installing Vulkan on a Windows-based machine with a Vulkan-capable GPU. Tutorial number 13 is installing a bunch of examples. Now, this example is not ray tracing, so your GPU does not have to be ray tracing in order for you to run it. But if you want to be able to run the ray tracing examples as part of the example set that's installed with tutorial number 13, you need to make sure your GPU is ray tracing capable. For NVIDIA GPUs, it's RTX models and later. Okay, but yeah, let's get into it. So I have so we're still on the render function, which is rendering things to the screen. And basically, when we run the application, we have a canvas that falls onto a sphere, right? And you see the sphere there, and the canvas falls on it, and we get this thing, and then we get wind. Okay. This is, if you've been following on this synchronization hell series, you know this already. Okay. And we're in the render function. All right. So we are dealing with the render stuff. Now I added a handful of things, a couple of things to this render function, just so you guys can get anchored into exactly what we're dealing with, and you guys actually believe when I say stuff, right? Because we've been discussing a lot of stuff in the render function, but we haven't actually seen any real effect visually. We've seen effects with the validator. We've seen effects, when we change the semaphores and we get errors and stuff, but you haven't really seen stuff visually. So I kind of want to anchor you guys into a visual sense, so that you could sort of, really try and follow along with everything that's going on. So in order to do that, we have to, so what I did is I added in this time delay. Okay, so this is a time delay that basically delays each frame that is actually happening, each frame for the render calls, right? So it's delaying each frame by some time. So if we look at when we don't have this delay, we get our render at 15, over 1,500 FPS, right? Or somewhere about there. Okay, so we're getting a lot of frames per second, FPS, frames per second. You video game guys know exactly what we're talking about, frames per second. Okay, but we're gonna add in a delay in it, and we do it by adding in this string right here, and then also, we add in these two includes here. Okay, so we add in the delay, and then in order for this to work, we have to add in the includes at the top of the file. Okay, and then when we do that, what we notice is that you're gonna see now the FPS falls, and we see that everything slows down, right? And that makes sense because we are delaying each frame that is being rendered. Okay, so this is the render function. We are now delaying each frame that is being rendered, and you can see everything going in slow motion. So this is just to anchor you guys to, we're talking a lot about this function and the semaphores and the now we're going to talk about the fences and stuff, but it's almost like you guys don't believe me, right? So I put in this delay here so that you guys understand that that's actually what's happening. Now if we increase the delay, If we increase the delay, what do you expect to happen? You're going to see that it goes down even slower, and you notice that the frames per second is smaller, right? So we were at 11, 12 before, whatever. Now we're at 6. You see, and it's just absolutely slow. This is not an A-list game. This would not qualify as an A-list game, and no one would play this game because basically it's too slow, right? And you know, it's not taking advantage of your GPU and all its capability, right? So just to anchor you guys to understand, and then of course, if we do, you know, if we increase it even further, you're going to see that it's even slower, right? This kind of there's a limiting factor to this, but basically you could see that it's really, really slow now, right? So you guys get the picture, right? So this render call is actually doing stuff, right? We're not just talking about something that we have no way of really seeing. And of course, if I lower it, if I lower the delay, we get a faster render, right? So we get a faster render, right? And notice that the frames per second increases, of course, and we get our faster render, okay? If I go even faster, we get a faster render, right? So these are actual frames that are being generated, okay? So you see now we're at something a little bit more manageable. Everyone, 60 frames per second normally is what is considered normal. If I go even lower, then we get into you know, we get into, you know, higher frame rate, right? But even even this lower 2 thing delay is still something, because if we remove the entire thing, now it goes really fast, right? There's no barrier at all, right? It could just go as fast as we could process, right? And you see how the frames per second increases naturally, okay? So we see that, right? We kind of inherently understand that, right? I'll just leave this at 100. Again, if you want to add this into the example, you need to put this string in here, and then at the top you need to put in these 2 includes, okay? And then you will get to what we need to do. Okay. All right, so the other thing that I wanted to sort of talk about is the fact that we have these fences here, right? And it was hard for me to really, you know, understand logically, you know, why the fences are the way they are, and why they're different variables and stuff. I mean, isn't render just one blob? Why do you have 2 separate fences with 2 separate variables for, you know, for the command and the graphics, right? But really and truly, what's happening is that when render is called, you know, when render is called, yes, it follows the processor follows this logic, right? So it starts here, and then it goes here and here and here, and then I think if I even tinker with this, I will get basically a blank screen. Now it runs, you know, I don't get any errors, but I get a blank screen, and that makes sense because we basically just returned, right? When we call render, it returns, right? But then you know, it's prepared, so it's not going to return, and it's actually going to give us the renderings, right? So remember, render is frames. We have frames that are lined up, and it's going into the swap chain, and you know, the frames are being drawn on. They are acquired from the swap chain. They're drawn on. They're put back into the swap chain, and then they're shuttled to presentation. We talked a lot about this in the previous video, in part 2. But now we have to talk about the fences stuff, right? So semaphores, as we know, is 2 processes on the GPU, and we have to manage synchronization between the 2. What I mean by synchronization is one happens before or after the other. The 2 of them can't happen at the same time. while one process is being done, we have to prevent the other process from being attempted to be done, right? So you can't draw on a frame that you can't compute on a frame. You can't compute and draw at the same time. You're either doing compute stuff or you're doing draw stuff, right? And also on the graphics to the presentation side, you can't be drawing on a frame that you're actively presenting to the screen, right? So that's what semaphores are for. But for fences are CPU to GPU synchronization. So we have CPU submitting stuff to the GPU, and the GPU does the work, and then the GPU returns to the CPU to say, hey, I've done the work that you have requested here. Here is the results, or basically I'm finished. And then the CPU can go ahead and request another batch of work or another task to be done by the GPU. If you don't have fences, then basically the CPU is just submitting tasks continuously, and it is not it is not mindful of whether the work on the GPU or the work requested is done or not. It just keeps submitting. So it's just basically a rapid fire submit work, submit work, submit work, submit work, submit work. But you have no idea, the CPU has no idea whether the first or the fifth or the seventh submission is actually completed, and it just keeps submitting and submitting, which is, obviously doesn't work, because you're eventually going to run out of RAM. You're going to run out of just resources and processing, and you also have to keep track of all of those submissions. So in order to organize it, we have a thing called fences, which synchronizes between the CPU and the GPU. So CPU submits to the GPU, GPU does the work, and then signals back to the CPU through the fences that the work is done, right? And that's what fences are. The thing about it is that for our render tasks, we have compute stuff and we have graphic stuff. So we have to compute the canvas and the canvas falling on the sphere, and how the canvas changes because it's falling on the sphere. All mathematical stuff. You also have graphic stuff. So you need to draw. After you've computed the mathematical stuff, you need to draw stuff, right? So we have two threads going on at the same time, two lines of commands going on at the same time. And because of that, we have fences to organize things, right? So we have a fence for the compute stuff, which is compute.fences, and we have fences for the graphic stuff, which is wait fences, okay? Notice also that for each one of these, so right now, literally what we're typing out here, this is on the CPU. Our source code is on the CPU, right? We're typing on the CPU. I'm highlighting this text, and I'm highlighting this text on the CPU. Okay, we only get to the GPU once we do this VK submit. Okay, so VK submit, lowercase VK, as you guys know, anytime you see a lowercase VK function in Vulkan, it's serious business, right? We're actually doing something in Vulkan, right? So we're submitting VKQ submit. We're submitting this work now to the GPU, but notice that we explicitly outline the fence for this process, okay? So for the compute submission, so we're submitting compute work to the GPU, we explicitly outline compute.fences, right? So we have our fence here. We did all of this work up here to basically say, okay, we're gonna set up our VKQ submit, and we're gonna add in our fence that helps us to organize the submissions from the CPU to the GPU for work to be done, okay? And we notice that we explicitly add it to the call. Now notice that it's so important that we actually have parameter space. So this is one parameter, another parameter, another parameter, another parameter for the VKQ submit function. But it's so important that we actually have an explicit space for the fence portion of the function call. Notice that this fence is not collapsed into the submit info, right? It's not collapsed into the submit info. It's actually its own separate parameter for VKQ submit. I don't know if that's that's really important. Now, these are the fence. This is the fence, right? Notice that the semaphore, though, The semaphore is sort of wrapped up into the submit info. So all of this thing right here is submit info, right? Submit info information. Notice that the semaphore stuff, the weight and the signal and all that stuff is collapsed into the submit info. That makes sense because as far as the CPU is concerned, the CPU is going to prioritize its business first, right? So it's going to have an explicit space for the fences, but the submit info and the semaphore stuff, that's all GPU stuff. You are basically applying rules to the GPU about how you go about doing GPU related stuff. So we have our semaphore stuff collapsed into submit info, but the fence stuff we have as our explicit parameter call for VKQ submit, okay? So this is how work is submitted to the GPU from the CPU, okay? And, we have this VK wait for fences and VK reset fences. We'll get into that, but let's stick to the VKQ submit first. All right, if we look on the graphics side of the equation, we also have a similar situation. So we have VKQ submit, and then we have wait fences as its own parameter to submit the fence for the VKQ submit, right? This makes sense, right? We're submitting graphics work to the GPU from the CPU, and we have to explicitly manage submissions from the CPU to the GPU, right? So just like for the compute commands, we also have the same thing for the graphics commands, right? You guys follow that logic? We have the compute commands and we have the graphics commands, and we have fences related to each of them. Just a little bit of housekeeping while we're on the topic. Notice that we have our render function here, but then we have these parentheses, right? That blocks off the compute stuff and blocks off the graphics stuff. That makes sense because we have basically we're trying to section off the scope of the variables. So notice that submit info is being reused here and it's being used here. Okay. So they're being used here and here, right? But we section off all the variable scopes, for each section, right? So this submit info is not going to be confused with this submit info because we have these parentheses. It's just it's a minor thing, but it's an important thing that I needed to really investigate in order to fully get a understanding of what's going on. So we have these parentheses here to just maintain scope. The other thing too is that notice that the fences for the compute and the graphics are different variables. Now, the definition for the compute fence and the definition for wait fences, it's actually done in different places. So here, this is done in in line 81 for the fences, right? For compute fences, right? But then for the wait fences, it's being done in the Vulkan example base. I don't really know why this is the case. It's not really a focus of my attention right now, but just know that the variables is two separate fences for separate things. And that's important because these things can be, you kind of want to section off, compute command submissions and graphics command submissions, right? You want to section it off. I was wondering, well, why not just have one fence for both of them? But it's going to complicate things because you also have to understand that queue families, they may be separate, but they may be similar. I mean, they may be separate or they may be the same queue. So, it complicates matters. And, we need different fences for different processes. Not necessarily in this case, but in other cases, you might have compute and graphics working parallel simultaneously. It doesn't happen here, but it could happen in other situations, right? So it's not like you could just have the render function and just have one big blob with the compute stuff happening first and then the graphic stuff happening after. You kind of want to section stuff off with the scope, and you want to have different set of fences for different set of things. This fence might be waiting while this fence is in reset mode and all that stuff, right? So we section off one after the other, right? So we have our VK wait fences, right? And then we have our VK reset fences, okay? So what happens is that the first thing is that we have our VK wait for fences, right? And we're basically looking for, we're basically, you know, where is it? Compute fences. Hold on. Right. So we're basically waiting for you know, for this to say that it's complete, right? So what happens is that, you know, initially, I guess, you know, this is in you know, ready state. So we do VK, you know, VK wait for fences. Then, you know, VK compute dot fences might say, you know, it might be in a signal state. So a signal state means that the process is done. So when we submit VKQ submit, right, we add our fence here, and it is in an unsignal state here. Okay. Then once the GPU says, "Hey, I've done this Q submit work. I've done this work that you've given me," this changes from an unsignal state to a signal state. So when it's in a signal state, then this process knows that, okay, the fence is now in a signal state. We can proceed with what we're needing to do because the work has been done. Once we proceed, once we know that we can see, the first thing that we do before we do anything else is we reset the fence to an unsignal state. Why do we reset the fence to an unsignal state? The reason we reset it to an unsignal state is because we're going to have to submit this fence again to the VKQ submit, right? We're going to have to submit this fence again to the GPU to say, hey, I have this piece of work for you to do. When you do the work, here is the fence that you're going to change from unsignal to signal, right? But you can only do that if you reset the fence to unsignal. So here the fence is signal, which is basically saying, hey, I've computed VKQ submit. You're now free and clear to proceed with the rest of processing. If this is still in an unsignal state, this does not move, right? We stop here until the GPU has done its work and it's now signaled that, hey, we've done our work, you can proceed. So it stops here until we get a signal state that, hey, the work is done and we can proceed. The first thing we do is we change back the fence to the unsignal state, and then we submit it to the compute fence, right? We submit it to the VKQ submit, right? With this in an unsignal state, right? So if we let's see, if we basically, you know, run our application, we see that we get no errors, right? We just get this thing, which is a conversation between a Vulkan and NVIDIA, okay? So we get no errors, okay? But if we now, let's say we refuse to reset the fence. Let's say we refuse to reset the fence, right? Just on the compute side, okay? So let's, I gotta rebuild computecloth because the Vulkan validator needs the Vulkan configurator needs the build file, right? So we're gonna not reset the fence, right? We're gonna not reset the fence. So we're not gonna make this unsignaled again. We're gonna keep it as signaled, and we're gonna attempt to submit the fence again, but it's already signaled, right? So here is, well, I don't even get the application doesn't, it like the window pops up, but it doesn't even run, right? But if we look into what the error is, don't worry about this. This generally comes up, whatever. But if we look here, VKQ submitted in signaled state. Fences must be reset before being submitted. The Vulkan states if fence must be unsignaled. Okay, Vulkan is going to be opaque as it is, right? VK fence submitted in signal state. Fences must be reset before being submitted, right? So you see, I'm not lying to you guys. We have to reset the fence in order for we have to reset the fence in order for all of this to be done, right? We have to reset the fence in order for our VKQ submit to proceed as needed. Okay, so VKQ submit, we have to we have to reset the fence, right? And the same would now it runs fine, right? So the same would happen for this guy, right? If I just didn't if I didn't do the if I didn't reset the fence, we would have the same issue where this is going to complain that the VKQ submit was submitted with a signaled fence instead of an unsignaled fence, right? So it doesn't even really run, right? So I'll just so this is the new, so it's the same thing. Submitting signals, say for instance must be reset, blah blah blah. Fences must be reset. You know what I mean? All of that stuff. Okay, so we get the drift, right, guys? We have to manage that process, right? So you guys now understand the idea of fences, right? We're submitting work to the GPU. Now, I also had another question about this render function. Okay, so the question was, okay, we have this render function. What happens if I because obviously you want to compute stuff before you could draw stuff, right? You need to compute how the cloth is going to move. You need to compute how the cloth is going to change as it falls down onto the sphere. You need to know how it all works, how the wrinkles and stuff of the cloth, right? So I was like, okay, what if I just, what if I took this graphics block? What if I took this graphics block and just basically moved it above the compute block, right? Wouldn't things go haywire? Because now you're trying to draw before you're trying to compute. But the problem with that is that it would still do compute before graphics. It still would do compute before graphics because let me launch it in the validator. Wait, I am getting an error. Hold on. That's not cool. I'm not supposed to get an error. Let's see, guys. We're doing some live. Okay, wait. Let's start with this. So we're rebuilding the file and everything. We do get our thing. Let's launch it. Okay, so we're back to where we were, right? But then now, if I take the graphics stuff, and I put it here, right? No. We should, everything should still be okay, but maybe it's not. Maybe my logic was right? But it runs, right? But we still get an error. So the error says, don't worry about this stuff. This is like other stuff, right? Okay, all right. So this is Q family ownership transfer, right? So this actually was this actually was what I expected. But like when I did it the other day, there was no error. But this makes sense. So we're running the render function, but it comes across the graphics command stuff before the compute stuff. Let's see if we can. I don't know if this is gonna do anything, but it's only gonna happen for the first. I just need to do it for the first. Yeah, but this is not gonna work. Yeah, that ain't gonna work. That ain't gonna work. No. Okay. So maybe my initial logic is right. So the thing about it is that you don't want to submit graphics work before compute work, right? So when you call render, you want the compute stuff to run before. Yeah, I'll have to investigate this thing. But okay, so when we run the render, we have to make sure that compute stuff happens before. I could have sworn that yesterday it didn't do this. It had no problems with this thing. Let me just try it one more time, right? Because I thought the semaphores would make sure that compute happens before graphics, but that is not the case. Right, we get our no way to be signaled. We get the no way to be signaled error, right? So I guess my initial logic was right, because I was trying to basically move the compute commands first, and I'm like, how could you draw stuff if you haven't computed it first, right? So we do get the error, but what I think happens is that it just does the draw of the previous frame or something. But when we call render, you respect sort of the layout of what comes first. So compute comes first and then graphics. Within the compute and the graphics submissions, we're talking from CPU to GPU. We have our own set of rules, right? And then notice that, you know, I don't want to get into it now, but we're dealing with frames, right? So frames, current buffer, right? We're dealing with the current buffer, right? So a compute commands submission for, like, say, frame 5 and a graphics command submission for, say, frame 5. I'm going to assume that once those commands are now in the GPU, right, and we're dealing with two processes on the GPU side with you know, with semaphores, right, with semaphores, that now the GPU is going to adhere to the rules of the semaphores, right? So we have two processes. We have a submission of compute commands with its own set of fences and a submission of drawing graphics commands with its own set of fences. And then on the GPU side now, we have you know, we have semaphores. We have semaphores that deal with how the work is being done, right? So that is organization. That's organization for you. We have the organization using fences for the CPU to GPU submissions, right? The queue submissions, right? These are the fences for the CPU to GPU thing. And then once these both now, because remember, the processor is going through all of this stuff. Once this process is in the GPU, these commands are in the GPU. Once it's in the GPU for the compute and the graphics, once it's in the GPU, now we have now we have to deal with, you know, what gets done when, and that's when the wait semaphores and signal semaphores come in, right? So this is the GPU side stuff, right? The GPU side stuff with the semaphores, CPU to GPU side stuff, right? The fences. Okay, so you guys naturally understand how this stuff is actually going, right? This actually was a very good thing. Once I put back the correct order of things, with compute first and then graphics next, you know, everything lines up properly. I was curious. I'm still a little curious though as to why when I move the graphics commands above the compute commands, that you know, we get that error. Right. So when we launch now, we get our thing and we get our thing. Right. That's fine. I think this is complaining about the semaphores though, right? It was complaining about the semaphores. So if we, right, if we do this, I just want to do it one more time. I think this is a semaphore complaint, not a fences complaint. It's a semaphore complaint. So yeah, that was my bad. It's a semaphore complaint. So if it's a semaphore complaint, then it's saying that if it's a semaphore so we get it running, but then it's a semaphore is that it's this is actually a buffer, so it's a memory thing. It's not okay. So this guy is waiting on semaphore that has no way to be. So this is like on the GPU side. Okay, so it's a semaphore problem and then of course a buffer problem, but let me think this thing through. So we know that we're waiting for compute to be in a complete state here. But then when you get down to here, it should be in a... Yeah, so I'll have to investigate that a little bit more. I thought it would have been okay. And that's why I was saying that, like, you know, this what I wanted to say was that there would be no errors because the semaphores would you know would take care of what gets done first. But I don't know, man. I'll have to investigate that a little bit more. All right, but let's just make sure that we are back to where we said we were. Back to normal. I'm going to keep in this delay thing just in case I need it for a future thing. But yeah, let's rebuild this thing. And then let's see if we get... Right. So we get that little error thing, but yeah. Okay. Right? We get back to normal. Okay, so we're good there. All right, so anyway, guys, that was the discussion of the fences, discussion of variable scope, discussion of you know, we have to, if we take out the reset fences, you know, we would get into problem. I could also, I think this crashes when we do this. I think it crashes when we take out, you know, we don't even have a fence for the submissions, right? So think of render as being constantly being called, right? Render is always being called, but you have to proceed with render in an organized fashion, right? We're always calling. Remember that frames per second, it's like, it's a serious thing, right? So it basically shows the initial picture, but then it basically crashes, right? And the picture that we get is this guy right here. Yeah, fences must be in an unsignal state, blah blah blah, must be reset before. Yeah, so we get an error, right? So we need to actually, you know, use fences to... So we're going to rebuild one more time to make sure that we're back in a regular state and that we're back to baseline and that we're good. But yeah, this was a very good video, guys. So you guys now understand, you know, fences, variable scope, and even like a little bit of order of operations. So we're back to where we were before. We don't get any errors. We're good to go. All right. So again, guys, tutorial number 1 and tutorial number 13. 1 is for installing the Vulkan API. 13 is for installing the examples. It's a CMO Windows-based machine with a Vulkan-capable GPU. If you want to run the ray tracing examples, you need to make sure your GPU is also ray tracing capable. This example is not using ray tracing features. Okay, so you'll be able to run it without having to worry about ray tracing. Thank you guys for watching. Have a great day.